Okay, today we're going to look at area and definite integrals, and I would like to revise a little bit what we've looked at so far. We started the chapter by looking at some curves. Say let's a curve fx, and the question was, well, given a certain formula, can we find the area between the curve and the x-axis, the area under the curve? And it turned out that, well, sometimes you could use your DDC for that, but it turned out there was like a kind of magic function, which we called capital Fx, and by just filling in the boundaries, suppose that you take A and B as the boundaries, once you had this magic function, by taking Fb minus Fa, you would straight get this area between A and B. And, well, the magic function, it turned out to be the antiderivative, so you need to find a function, capital F, so that if you take the derivative you have Fx. Yes? And the notation that we used many times was, okay, we're integrating from A to B Fx dx, those are the boundaries, and then finding the antiderivative, you have Fb minus Fa. This is an example of a definite integral because there are some boundaries involved. But what if the f is not always positive? So in these cases the f was always above the x-axis, but you can imagine a situation where the f is negative or maybe partly negative. So how do we deal with that? So let's look at an example where you can also involve some geometry. Suppose I have something like fx is maybe half x minus 1. So we can sketch the graph. So it starts at minus 1 and 2 zeros and x-intercept something like this. So y is half x minus 1. And also here we would like to do some integration. Suppose we want to find the definite integral. Let's say from 0 to 3, half x plus 1 dx. Okay, notice that the graph is partly under the x-axis. So this is 0, x, y. For x is 2 it's 0, and for x is 1, for x is 3, sorry, it's going to be half. Yes? So, well, what is the area under the curve? Well, you can say, well, there is a positive area there, but there is also a part below the x-axis. So what happens if you do integration? Well, if you look at this first part, from 0 to 2, you'll definitely find a negative answer, because the f values are below the x-axis. And for this part, you find a positive answer. Yes? So, if you look at these areas, we can use geometry to find these areas. That's no problem, because we have two triangles. So this triangle, the base is 2, the height is 1. So you have there area 1, you may call half times 2 times 1, it's 2. And this one, base is half, the height is, sorry, the base is 1, the height is half. So half times 1 times half, so that area will be 1/4. So what happens if you want to calculate this integral? Well, you find a positive area of 1/4, a negative area of 2. So it turns out that the total will become 1/4 minus 2, it's minus 1/3/4 or minus 7/4. We can of course check that by doing the calculation, and we are able to find the antiderivative there. So you can say, if you write down the antiderivative, 1/4 x squared plus x, and then the boundaries 3 and 0. If you fill in 3, you have 9/4 plus 3, that's 9/4 plus 3, that's 2/1/4. Let's see, 9/4 plus 3, 5/1/4. Oh, it should be half x minus 1, of course. So then the antiderivative is minus x, so we have 9/4 minus 3, and that's the minus 7/4. So also, if you just do the calculation, you take the antiderivative, you fill in the boundaries, you find a negative answer. So remember that if the curve is above the x-axis, the area will count positive. If it's below the x-axis, the area counts negative. So let's turn to this example. Suppose this is some curve fx. So it consists of 1, 2, 3, 4 line segments, and we are interested in finding the definite integral fx dx and the boundaries from 0 to 8. Well, you can clearly see that some part of the curve is positive, so there is this positive part, and then also there is a part above the x-axis. So in order to solve the problem, we need to use some geometry properties and try to find the two blue areas. They're positive, and then there is a negative area there, and then we add up the two blue ones and then subtract the red one to find the area. So you can do a little math there. This is 3, 2 and 6 minus 4, so it intersects the x-axis at, let's have a look, at 4. So you can, for example, divide it into two triangles and a rectangle, and then it adds up to, this is area 2 times 2 divided by 2, so this is area 2. There's an area of 2 for the rectangle, and then 1 for the triangle. So that adds up to 5. And then we have a triangle here. This is intersecting the x-axis at 7. So we have base 3 and height 4. 3 times 4, 12, so that will be an area of 6. And this one we go 1 to the side and 4 up, so that's an area of 2. So if you divide them in 3, so that A1 here equals 5. The A2, the negative area, equals 6. And then there is another area of 2. So finding the total area, we take 5 plus 2, the positive areas, and we subtract 6, the negative area. So we find 1 as the definite integral here. Okay, so that's an example of definite integrals and how they are related to areas.